So now we're going to have the presentation that we were scheduled to have before. We're going to have Don Brady and Justin Gibbs talk to us about fault management in ZFS.
Okay, thanks. I'm Don Brady. I'm from Intel, and I'm going to talk a little bit about fault management today. And let's see. Yeah, let me go through there. So I'm basically just going to do a brief history, and then try to go at a high level, 10,000-foot view of the architecture and sort of the implementation. And then we'll go into some specifics, and Justin's going to help me talk about what's going on in FreeBSD and fault management, and I'll talk about the Linux. And then I'm hoping that we'll have some time at the end for future directions. This is, for me, when I got involved in this, it's a lot of work that just sort of stalled out in 2007, and I know a lot of private companies have been doing some of this stuff, so I'm kind of anxious to get this stuff moving again inside OpenZFS. So in terms of the history, originally in ZFS, circa 2005, when it sort of went live, there was no real disk handling. Drives were only, they could be in two, it was binary mode, they could be in two states. They would be either faulted or they were fully functioning. So at about that time, FMA was landing, and so there was an effort to make ZFS visible in that FMA space. And it turned into sort of a roadmap, and they added diagnosis and basically spread it out over several years. As they got more familiar with the territory, they started adding items to the roadmap to fill out the stack. And some of the features never made it back. I sort of alluded to that. Like tying generic I/O faults, smart data, telemetry. Some of that data is not actually being fed into the diagnosis engine. So that's one of the things I'm hoping we could sort of renew that effort. Most of this history I gleaned from Eric Chirac. I talked with him, and he was sort of the instigator, I guess, of some of this stuff. And at Fishworks, he was actively involved with bringing FMA, full FMA, like sort of support into ZFS. Let's see. So yeah, so my overall goal for this talk is to sort of renew that stage roadmap approach that they were following before. If you look back into the history, there was a phase 0, a phase 1, a phase 2, and I frantically have Googled for phase 3, but I have not been able to find it. So we'll have to invent that one. So yeah, like I said at the end, and then maybe even tomorrow a breakout if people are interested in that. So this is sort of a simplification of fault management in ZFS. Sort of shows all the key players. Overall, the idea is automated diagnosis and isolation of a fault of a VDEV. A fault is something we can associate with an impact, like loss of redundancy, and then there's a corrective action, onlining a disk, replacing a disk. The fault management stack is basically comprised of error detection, which is sort of that middle section, and then a disk monitor is a key player at the top, and then there's 2 response agents that are actually responding to any diagnosis going on. So in normal operations, the kernel module will send an event, and there's a userland daemon that will respond, and each platform actually has one now, which is nice. So in Solaris, that was the FMD, and in Linux we have Z, and then in FreeBSD they have ZFSD. So these daemons will sit there and listen for events, and then feed them off to the different modules based on subscriptions that they take. And then likewise, there's a disk monitor implied, and this is very platform specific. but it's available on every platform. So basically, you have to tie into this disk management stack. On Linux, for example, we tie into libudev to see disk events. So it's sort of at the core of this fault management stack is what we call the diagnosis engine. And it consumes raw telemetry from, in our case, in the simple case, just from the kernel, checksums or I/O error reports. And then it provides a diagnosis. These errors come in, and then the engine per VDEV will associate a case. A case is sort of like a case file for a detective. It'll actually open a case, and in the case of ZFS, we attach a CERT engine. A CERT is just a fancy way for saying software error rate discrimination. So we're looking for N events in a T time period. And these varies across platforms, but it's typically on the order of like 15 errors in 10 minutes or something to that effect. And this was what was chosen. I didn't actually ask Eric why these numbers were chosen, but these are the same numbers essentially that we had in 2007. And I'd be interested to see, from experience, if people have seen where these numbers weren't adequate or not aggressive enough or something like that. So basically, in summary, for the diagnosis engine, error reports that come in are sort of the symptom, and the fault events that come out on the right side there are the diagnosis. And so it'll spit out they call them suspects, but a fault will come out of there. Then this is where the retire agent kicks in. It'll respond to a given diagnosis from the previous diagnosis engine, and it'll take certain actions. It can mark a VDEV, it can replace it with the spare, and let's see. Yeah, so it'll replace it with a spare, and currently I think what's in the top of ZFS OpenZFS tree is real simplistic. It just takes an array of spares, typically global, and it'll try. I have a faulted disk. Let me try the first spare and see if it works. And so I know for a fact that people want to have a better matching algorithm. We now have the capability of having different tiers of like, for example, metadata, and you might want to have a separate spare for that. And in the case of D-RAID, which Intel is working on, it's a declustered RAID solution. It actually has virtual spares. So that's another special case where you'd have to actually have criteria for matching the spares instead of just blindly trying things until something works. Okay, so then this other agent, and I took the liberty to call it the disk add agent. In Solaris, it's called ZFS Module, and that just doesn't resonate very well. It came out of the SysEvent loadable module framework, and for various reasons, it was implemented that way, and it's fine. But in essence, it is an agent. So I took the liberty to call it an agent, and that basically will consume the disk monitor events. Like if you get a disk add, the disk agent will see a new disk, and it'll try to match it against any imported pull to see if it's missing. The most obvious case is online. If you had a late responder during your import, or if a disk went offline because somebody unplugged it and pushed it back in, this agent will actually see that disk, notice that it belongs to a certain pull, and place it back online. The other actions provided by the disk add agent is this concept of VDEV replace. And I think it's important to note that auto replace is different from auto spare. So sparing is part of like the previous agent I talked about, but auto replace is this concept that sort of came out of that chassis Fishworks things, where you can actually just take a disk out, whether it's for maintenance or retirement, and put in a new disk, and the auto replace will automatically detect it and notice that you opted in, and it will replace it. It'll actually reformat the disk, put it back into service. So it's like actually magic. You can take out a random disk out of your pool, stick in a totally different disk, and ZFS will automatically make it good, and you know, as soon as the resilver's done, it's a brand new disk in there without having to actually sit in the command line and type, you know, offline and replace and all that. So this is actually available in essence on all the platforms. As I mentioned, each platform has a daemon that's sitting there looking for events. And what's sort of missing, and we can talk about this at the end, is sort of the diagnosis and the retirement agent and the add agent. There's various levels of support across the different platforms. And one goal, I think, would be to get everybody on parity to what I described earlier, and then we can go and start adding diagnosis improvements and predictive, better prediction of when a disk is going to fail or has failed. So at this point, I'd like to have Justin come up and give us a overview of what's going on in FreeBSD.
Do you know if my slides are right here?
You just have to go forward. Sorry.
Oh, keep going. Which way am I going here?
Just the right arrow.
Excellent. Okay, so the support in FreeBSD I'm going to talk about was developed by SpectorLogic. I'm no longer working at SpectorLogic. Neither is Will Andrews, but Alan Sumners is there, and the poor soul is trying to upstream all the work that we did while we were there. You'll see pull requests from him in Illumos. In fact, I saw some activity from him, I think, today. Some of the things that I talk about in these slides, the majority of them have been upstreamed into FreeBSD. There are a few outliers. And those, I think, are mostly going through Illumos and then coming back to FreeBSD that way. Okay, so as Don talked about, there's kind of a simple description of what you want this event daemon or this fault management system to be able to do. It's supposed to be able to detect drives that are in a bad state. That could be either degraded or faulted. In ZFS, degraded means that the kernel will continue to use the device. It will continue to read and write to it. But it's kind of like a notification to the fault management system that this is an ailing drive that should be retired. A faulted drive, though, is basically taken out of service. Whenever we detect these drives, assuming that we have spares available, we want to activate spares for them. If somebody decides to pull a drive out and shove a different drive in or shove the same drive in, we want to detect those events and make sure that the drive comes back into the pool. And in these situations where we have like replaced by physical path, which is this magical thing that Don was talking about, where you have an array that has physical path information, you pull out a drive, you stick in another drive that is of similar capabilities, similar size. The system basically just detects that, decides to aggregate it into the array and bring it online. And this last part, deactivating a spare after a successful resilver, that's in the case where you have activated a hot spare, and for instance, you went and removed the original failing device and replaced it with a nice healthy device. The system resilvers back onto the original device in its original physical location, and at that point, we can return that spare to the spare pool. That's deactivating a spare. In most cases, the deactivation is supposed to occur in the kernel, but as we found in the development of this work, there are cases where that doesn't happen. And I'll have more about that in a later slide. So one of the challenges that happens in trying to make this all work is that we have events that come from different places within the kernel. And in fact, in the Illumos Solaris implementation, you have system events, and then you have e-reports or error reports. And they're kind of considered two separate namespaces, sometimes going through different systems. And yet, in order to be able to be successful in managing one of these faults, you might need information from all of these different places. And you have to actually aggregate it correctly, even if those systems have different latency properties or might deliver the information out of order. All the information here that we need are the sys events, the e-reports. We need to know the physical path information, which might be coming from different devices in the system. So, for instance, I attach a drive. It's coming through a SAS HBA or maybe a SATA controller. But the way that I know where it is comes from an enclosure device, which is being run by a totally different driver, which might report its data out of sync with a device arrival or departure event. In a block diagram here, I'll give you a sense of the other systems in the FreeBSD kernel that we're using to get this information. So some problem areas that occur because of the asynchronous and distributed system that we're trying to manage here. So when things happen in the system, and in the ZFS case, that could be coming from a user-initiated command, like adding a device or deleting a pool or manually onlining a device or doing a replace. Those events, in FreeBSD at least, seem to come out well in advance of when you could actually issue an ioctl and see that pool state in effect. So we have to actually aggregate this information, detect the fact that we can't act on it just yet, and then rely on another event that comes out of ZFS to let us know that we should try again. In the case of hot device removal, usually that happens because our users are special. That usually happens when the device is actively being used, right? So we're sending IOs left and right to this device, and we pull it out. Well, what happens? It kind of looks like, because we see maybe some IO errors or whatever during that process, that this is a drive that's on its way out. Well, it is. It's just that it's completely leaving the building. It's not that it's dying. And so we have to be careful about how we attribute those errors to make sure that we don't decide that is a bad device that can't be brought back into the array when it returns. As I mentioned on the previous slide, physical path information, it can be, it usually comes from a separate device, and that device isn't necessarily always available in the system. If you're lucky and you have a nice Fishworks array or something from Spectral Logic, you'll have an enclosure services provider which will tell you, based on this SAS address or this SATA ID, exactly what slot in the system is being used. And you can do things like toggle the LEDs and everything. But it really is a separate system from the HBA that is doing the I/O path. And the events from it can, of course, come at different times than from your data path. Devices can degrade slowly over time, so we need to actually carry state. This state needs to survive across reboots, pool, import, export, things like that. And then events don't always happen, right? So I've run the system for a while. I have some things that go bad. I do some imports, exports, whatever. Events come flying at me. I turn off the system, and I turn it back on again. I'm at some basic state. And at that basic state, I still need to know, without having the event stream, what things are failed, what things I need to take action on, even if they've occurred while the system was powered off. For instance, somebody has returned the drive that went missing or added spares while the system was down. So in FreeBSD, the main systems that we're dealing with to be able to affect this fault management are, of course, ZFS with its streams of sys events and e-reports. It also has a nice ioctl interface, which is what allows the user space portion of the failure management system to affect change in the system. We also have this thing called geom in FreeBSD. That's where we get physical path information. Geom is kind of like a Lego brick system, which allows you to take a raw device or compose multiple raw devices, add partitioning, do volume management, all those types of things. And so the geometric nature of how it slices and dices and combines is why it's called geom. But we primarily use that for physical path information. And then DevFS is the way that we detect that a device has come or left the system. All of that information, all of those events, goes through devctl9. You can think of devctl9 as like the poor man's version of an event reporting system. Essentially, it predates JSON. It doesn't use XML. It basically is just strings of key value pairs that happen to come out this driver. And it was primarily done back in the PC card days, if you can remember those. So like you insert a modem or you insert an ATA controller in your PC card, and a script would run. When we developed this at Spector, we were thinking about doing a better event management system in the kernel. But as usually happens when you're trying to ship a product, you get to the point where things work well enough within your product, and then you get busy working on something else. But anyway, the stream of string data, is what you can really think of it. An event, which is just a key value pair in string data, comes through the user kernel boundary through devctl or devctl. devd is the generic daemon that can like fork off scripts if certain things happen. But we can actually subscribe to the event stream by also looking at its named pipe, and that's how ZFSD enters the system. Live dev dctl, the thing at the top of ZFSD, was our attempt to abstract away the event stream in its current format from what ZFSD has to do. So again, hoping that in the future, some better event stream would become available. Unlike in other systems, this is not a pub/sub stream. Basically, you connect to that named pipe, you get all the events. So ZFSD has to filter and deal with the fact that if it's too slow, it could lose events. And then at the very bottom of ZFSD, we basically use the normal libzfs, libzfs core libraries to be able to make our changes in the system. The case file repository is where we store information about devices that are in a slowly degrading state. Essentially, in FreeBSD, what that looks like is all the events that have been captured for that device that have not quite been sufficient to make it degraded. But it does basically allow you, during debugging and things like that, be able to see over time what has happened, exactly what events have occurred that has caused the case file to be opened. So here's a high-level state diagram of what ZFSD has to do. At the top, this is where we synchronize system state with the event stream. So we fire up, we go and we probe the entire system to try to figure out what's faulted and what's not. And while that's going on, we hope that we don't receive any events because we don't know where that event happened relative to our probe. So we sit in a loop until we basically get a clean scan of the system without new events that might change our view, our world view. Then we enter a normal event loop where we can process events from these different systems that I mentioned before. Because of the event flood that can occur, essentially we have to have this yellow diagram, the yellow diamond up there. We have to notice if an event has been dropped in our event stream. And essentially we modified devd, the daemon that feeds us data, to make sure that it would always close our pipe if it couldn't buffer an event for us. So essentially, if our stream gets closed, we have to go back to the main loop again, resynchronize, and make sure that our worldview is correct. The main way that we deal with or detect errors is through this path here. ZFS emits a VDEV event. That's a checksum error or an IO error. We look to see if we have an existing case file for it. If we do, then we can take that event, we can add it to the queue. And if we get to a certain number of them, then we can mark the device as degraded. And then we go and once we have all the information in the case file, we can try to evaluate the case and see if there's something that we can do. So if we have decided to degrade the device already, we can online a spare. But in most cases, what happens is if we have like just a single IO error, we'll open up a case file, it will sit there, and we'll go on our merry way. We have to also be aware of pool events. And these events are things that could be initiated by the user. They could add more devices. They could destroy a pool. They could do things like that. And essentially what we do is we take the pool GUID, and we can use that to look for all case files that are about VDEVs on that pool and look to see if we can now, with the new state of the pool, do something to rectify that particular problem. And then the last two, DevFS and Geom, that's basically where we detect that devices have departed or arrived. And the Geom event, as I mentioned before, we can get physical path information in a delayed sense because it's coming from a different device driver. So we actually, in both the DevFS handlers and the Geom handlers, have to kind of cross-check each other. If a device arrives and it has physical path information, well, great, we can do all the checking that we do with physical path information. If not, hopefully there'll be a Geom event later that will tell us, where it exactly lives in our chassis. So the last two boxes here are how we deal with things coming out of order. Essentially, as we process an event, if we go and look at pool information by doing ioctls into ZFS, and we can't match this event with pool state, we'll basically add it to an unconsumed event queue. And it will sit there until the next time that a config sync occurs. And config sync is a special event that is emitted by ZFS when it goes to write new config information. At that point, we basically give all of the unretired events one last chance. We process them all to see if they all match up. If they do, we take action. If not, we throw them on the floor. So we ran into a couple things while we were doing this work. Probably the biggest issue that we found were things around the way that spares are kind of bolted into the system. Both spare and aux devices behave a little bit differently than other VDEVs that are part of a config. They're attributed to a pool through a MOS object. They're not in the main label information. So a lot of the things that we end up doing that would affect something like a RAID Z VDEV or something like that, we just can't do for spares and aux devices. And Alan is probably the best person to ask about all the different, kind of torturous use cases that we did to be able to make these things break. But you can imagine things like, you have a pool, you export it, you move it into another chassis, maybe some devices get mixed around, including a spare. You activate a spare on a new pool, because that's certainly allowed. There's nothing that stops a spare from being added to another pool. It gets activated, and then maybe it fails, but you can wind up in these situations where multiple pools have pointers to devices, some of which might not be even in the system anymore because of the way that this accounting is done. The solution for Spectra was to only activate spares or only call things a spare when we decided we could actually use a spare. So we don't use the global spare pool in a Spectra appliance is basically maintained by the management software in the appliance. When we decide that something needs to be spared, we call it a spare just then, add it to ZFS, add it to a pool, and then the rest of ZFSD takes into effect. The one in the middle there, RAID Z a RAID Z of spare or replacing mirrors is also another interesting one. This one's pretty hard to hit. But essentially in ZFS, the expectation is if you have a pool that has parity information that you can always recover by doing some kind of, read from the other VDEV or reconstruct from parity or whatever. And that ability is done, at the top level VDEV layer. And for this reason, you usually can't make like a RAID Z of mirrors, but you can in this case. And when you do, if you try to read from a spare that has reports bad data, essentially there's not enough information in the stack to be able to force the read of the other member, which was kind of surprising. And lastly, what's missing inside ZFSD and FreeBSD is most of the stuff that Don talked about. This is basically enough to get a product out the door. We don't have things like the ability to take smart data and use that as a diagnosis engine. We don't have the ability to detect differences in performance between peers, to notice that a device is slowly degrading but perhaps not throwing errors yet. Physical path replacement works great as long as you have no partitions. And in an appliance, you can do that. But a lot of times users like to have GPT partitions and things like that. And if you don't have a really good physical path provider, you can't even do this magical spare replacement. So if you have a chassis that doesn't have an enclosure services provider, essentially you have to do the commands manually. ZFSD isn't able to do the physical path replacement for you. Yeah, so backwards.
Thanks, Justin.
I don't know which slide you want.
Nope. Yeah, so I'll just go through this quick. We're running a little bit short on time. But so on Linux, we have this thing called Z. I referred to it earlier. And basically, it's an event monitor in the user space. And basically, it'll collect or watch for events and send them out to any of these things we call Zlets that will listen to or that have subscribed to a certain event class. And then they can perform an action, typically send an email or do something like that. There's no diagnosis in the current state. However, we've had some recent developments, and we've sort of expanded the mission and added the FMA logic into Z itself. So rather than like on Solaris where they're run as separate plugins, we just basically bake that logic into that process. So then it can actually do the equivalent work that I referenced earlier with the retire agent, a diagnosis agent, an add agent. And so that's what we've been working on lately. Let's see, I think I have a, well, so that all the different platforms essentially have to do the same thing. They have to see a disk, and this is just sort of the basic schema that we've implemented, and it matches exactly what you would expect on Lumos. Basically, you have all the keys you need to make a diagnosis. So some of this stuff is landing. We landed that phase 1 work there, which is basically doing the auto replace and auto expand, that disk add agent, and then of course the disk monitor itself. And then we have some other stuff coming up in future. We're doing a work in progress. If anybody's interested in helping out there, please see me later today or tomorrow. And Justin touched on this. We really want the diagnosis agent to be smarter, so we need input from people on what they've seen, what are good metrics to look at to make it smarter. And then that's pretty much all I had. I have some resources here. You can refer to them later. But basically, the fault management, Mike Shapiro had a really good article in ACM about that, about what the goal was. And so reading that is insightful. And then some of Eric's blogs, and then, of course, the actual module sources themselves are pretty good at understanding this. So, do we have time for Q&A, or? Okay. I don't want to come up. So I'll just go back to that. Yeah. So basically, if there's any questions, but I'm really, we're really looking for input on people on how to make better diagnosis of when a resource is going bad. One of the other things we need to consider too is if you had a top-level VDEVs that were all like a single VDEV, maybe backed by some hardware RAID or something like that, you don't want to necessarily look at the errors and say, "Oh, I've had 15 errors, you're gone." When it's like, well, there's still a lot of there's diddle blocks. There's it may not be appropriate to take out the final, sort of VDEV. So, questions? That's a good question. That's actually a work in progress. We've actually, The question is, how do you automate this where there's a lot of hardware dependencies in this stack? That's a good question. We've actually been able to simulate removal and adding of devices in Linux, at least. And so we've automated the testing of auto online, and that's a start. There's already tests for auto expand in the ZFS test suite today, but that requires using zvols, and so zvols on top of ZFS, or ZFS on top of zvols doesn't work on Linux. So yeah, that's a good question, and we're working on that, and then hopefully we'll make some progress there.
So in the case of what Spector did there is, since all of our enclosures have at least an expander, we basically did most of our simulated device faults by disabling PHYs on expanders to be able to take out drives, basically without the drive knowing that it was going to lose connectivity. We also had, from a previous generation product, we had the ability to actually depower drives just on demand, programmatically. And so we could do things like that. And so you can imagine tests where you take out a portion of the drives, maybe you export the pool, you bring them all back, you try to do an import. All of those types of permutations were things that were possible from a programmatic standpoint, but it required, because we were doing it actually with the real hardware, it requires, a chassis with a significant number of slots and the software that would allow you to play with the PHY status. The ability to change the PHY status, though, is all upstreamed in FreeBSD. You can do it with the CAM utilities. The best thing that we were able to do there was basically just to collect all of our special drives. And special drives are the ones that you don't want anybody to ever take away from you because they exhibit really special behavior. And so, we had this pie in the sky idea of being able to do it actually with target mode simulation, because we had also another guy on staff who did a lot of target mode stuff. But we just never found the time to do that. But it'd be nice if you could basically just do the injection down there with, injecting ASC, ASCQ codes or whatever to simulate that a particular I/O failed.
The question was whether or not the Linux implementation, sort of closely matches what's in Illumos. And yes, that was intentional. I actually looked at the model of the diagnosis engine, a couple agents, and found it, even though it was derived from FMA, it really didn't have FMA dependencies. It was just a good model. So we adapted that, and in Linux, we were successful in getting all those key functionalities working, at least in the demos so far. So yeah, it's basically the same. And the idea is that we're doing other features. We're doing this feature called DRAID, which has these virtual spares. And so we want that logic to live and not prevent DRAID from going to OpenZFS, for example.
Right. So the question was, I mean, is it possible that through very special activation of spares that you could wind up with a pool that is now all of his VDEVs are bigger, and what prevents that from turning into an auto expand? And I think that is an optional feature, right? You can turn off auto expand.
Opt-in.
So
Yes.
yeah.
The auto expand is only on certain granularities. So even if you have auto expand on, it only expands full.
Yeah, it has to be a full like nice slab that you would add on.
Addition, yes.
Okay.
Like 10 megs bigger.
Yeah.
Pair.
Yeah, so just for the recording, essentially auto expand requires a certain amount of minimum space before it will do the expand. It has to be at least enough to be able to do another metaslab. And so if it's just a small difference, you're not going to run into that problem. And it is still an opt-in feature to have this happen.
We get around it by just using partitions. So we never use all block devices. And if the spare kicks in, we kick in the spare with the correct partition size. So it doesn't matter if the spare is a 6 terabyte drive and the block device it's repairing is 4 terabytes. It emulates the partition on the 4 terabyte drive.
Yeah, so the answer over there was that they do it with partitions. But I guess the question that I have then is, if you have partitions, you must not be doing replace by physical path, or you've modified ZFSD.
Of course, the latter.
Oh, and it hasn't been upstreamed? Shame on you, Josh.
Other questions?
So we had a huge problem with SAS instability spamming ZFSD and causing it to use up all the spares in the system. And a lot of times when you have SAS instability, the right thing to do is nothing and just stop. And so we had to deal with that. And then the enclosure affinity is another problem we had to deal with, where we try and replace a drive in JBOD 4 with a drive in JBOD 1, and pretty soon it's really hard to keep track of. Is there any thought about that kind of stuff?
Okay, so there were two questions there. One was, what do you do in the face of SAS instability, right? So SAS flipping around and injecting errors that aren't really related to the VDEVs. And in that case, I mean, I guess I need to see the failure. We chained up a lot of fairly large systems, but didn't actually see, I guess, the type of errors that you saw, because we tuned, the equivalent of the CERD engine for the Spector appliances based on that experience. So I don't know what the right answer is there. I mean, it may be that you can look at the types of error codes that are being returned and the behavior of the HBA to be able to discriminate between events that are really fabric related versus end device related. But that really gets down to the crux of, the point that I think Don's been trying to make, is that in these systems we have this framework for being able to do diagnosis and recovery, but it's just a basic framework. It's not complete, just as you found. And then what was the second one? Oh, right, a closure infinity. We didn't have a really good answer for that at Spectra. Essentially what we did is in our management platform, that's where we carried the concept of spare affinity. And it was basically the management system would detect that a spare was useful, and it would assign it to the correct pool at that point. And that's basically how we were able to make sure that the spares were used where we wanted them to be used.
There's one up here somewhere.
In a future world where ZFSD is aware of smart events, are you going to have to replicate all of the dictionary stuff that Smart Modules has built up?
Essentially what ZFSD, so the question was, if you were to add smart information into the diagnosis engine, right, in this case in FreeBSD or whatever, would you have to replicate the type of dictionaries and information that's recorded inside smart tools? As far as the failure system is concerned, it just needs the diagnosis, the output, right? It just needs to know, should I replace this drive or not? And so you just need a binary answer out of the smart tools. It's not that the diagnosis engine has to completely understand the smart data as long as some component in the system can do that. So I would expect that you just end up using the smart tools to do that.
Other?
Other questions? Okay, cool.
All right, thanks.